Hi folks, we're going to take a look at why we sometimes need to work with two equations to solve a problem. Okay, in other words, why we need to use a system of equations. So first we'll go back to what you would have done a lot of last year, which is solving an equation that has only one unknown. Okay, so whatever the scenario might be, I'll just make one up. Say we have 2x plus 3 equals 7. Okay, so we have a linear equation here, linear because the exponent on the unknown is just 1. Okay, and you know how to solve this equation. You can do it by guess and check, by figuring it out, or you can use an algebraic process, in particular working with opposite operations. So subtract both sides by 3 to isolate the 2x, and then divide both sides by 2 to isolate the x, and there you go. You have the solution to your equation. Okay. However, what if we have a scenario like this one here? Let's say you buy 10 pens, okay, and some of them are red and some of them are blue. And I ask you, well, how many of each did you buy? And you realize intuitively, well, there's more than one answer here. I could have bought 1 red and 9 blue. I could have bought 6 red and 4 blue. Okay, and in fact, you can make a list of all the possible scenarios, or you can represent this by an equation. So let's say the number of red pens is R and the number of blue pens is B. Well, then we can write R plus B is equal to a total of 10. Okay, and you realize here that you can isolate one of the variables, but you can't figure out exactly what its value needs to be. Okay, now in fact, this equation here has infinitely many solutions, because yes, you have 1 plus 9 is 10. You also have negative 0.5 plus 10.5 is equal to 10. But of course, because this scenario is related to items that can only be represented by integers, it limits the number of solutions. So you actually have a finite number of solutions to this particular problem, even though the equation itself has infinitely many solutions. Okay? So in this case, when we've got two unknowns, you're going to need a second piece of information. So this first equation involves the number of pens that we're working with. Okay, so the other piece of information could be given in other ways. In particular, they could tell you something about the cost of these pens. So let's say red pens cost $2 each and blue pens cost $3 each, and I spent a total of $23. Okay, with this information, I can again try to figure out all the possible scenarios. Okay, now I could say, well, 1 red pen and 1 blue pen, and I could figure out how much that is and see whether that equals 23, and then do that with 2 and 8. But you can see that that's going to take quite a bit of time. So in this case here, it really is worth working with the algebraic representation. So in other words, let's write an equation to represent this. So I spend $23 in all, and how do I spend this money? I buy red pens, so $2 for every red pen, and I multiply it by the number of red pens that I buy. So notice here, what's nice is that the variable that I'm using in this equation is the same as the variable in the other equation. Even though the whole thing is representing something different, cost versus number, I want to always work with the same variable in each equation. So 2 times R gives me the total that I spend on the pens, plus $3 each for each blue pen, and I multiplied by the number of blue pens. This gives me the amount I spend on the blue pens, and I add these two to get the total that I spend, which is $23. Okay, and so here we have a second equation using the exact same unknowns. Okay, and we're going to see that when we've got two unknowns, okay, two equations will allow us to solve it most of the time. Okay, we're going to see that there are some complexities that are going to come up along the way, but for the most part, two unknowns can be solved using two equations, as long as the equations contain those same unknowns. So the question is how do we solve this? Well, one way that you would have done last year is you realize, well, these equations both represent lines geometrically. So you could graph them and find the point of intersection, the R and the B, that work for both equations. We'll do that for a little bit. We're going to see that we're going to get away from that technique very quickly. Okay? You may have seen an alternative though. Okay? The nice thing about representing a scenario with an equation is that you can use the power of algebra to rearrange things as you like. Okay? So here, I've represented this scenario as the number of red pens plus the number of blue pens equals a total of 10 pens in all. Okay? But what I can do is, as we spoke about earlier, is isolate one of these variables, is rewrite this relationship in a different way. So what I can say is, well, how can I represent the number of red pens in relation to the number of blue pens? And of course, you use your regular old opposite operations here. So I subtract both sides by b, and the number of red pens can be represented as 10 minus the number of blue pens. Okay, so this unknown r is equivalent to the expression 10 minus b, 10 minus the number of blue pens. So now we can use this in our second equation. This variable r is the same as this one here. So this unknown r is also equivalent to 10 minus b. And here's where I can do what we call a substitution. And hence comes the name for this method to solving a problem such as this one. So what I can do here is I can substitute for this unknown r in equation 2 something that's equivalent to it. In this case here, 10 minus b. And lo and behold, what we have is now an equation in one variable, exactly like the one we started out with. And so we can now use our processes to solve this equation. Okay, so let's go ahead and do that. So here a little more complex than that one there. First thing we do is we distribute, so we can simplify both sides of the equation. So here we distribute, 2 times 10 is 20, minus 2 times b, plus 3b equals 23. Of course, we keep all the terms with variables on one side, and we'll bring all the terms that only have numerical values to the other side. So here we've got negative 2b plus 3b is just b. And then here 23 minus 20 is equal to 3. So we've managed to figure out that 3 blue pens were sold. Okay? But remember, we still need the number of red pens. But we have an expression that represents the number of red pens using the number of blue pens. I know that the number of red pens is 10 minus the number of blue pens, which I now know the value of. 10 minus 3, so r is equal to 7. Okay? So with these two pieces of information, I was now able to solve for the two unknowns in my problem. Okay? So just a recap here. When you've got an equation in one variable, okay, that can often be solved by these algebraic processes that we learned last year. We'll see later on this year, though, that as the equations get more complex, we're going to need to develop some new processes. Okay? But if we've got two unknowns that we're solving for, we're going to need two equations that involve those same two unknowns. Okay, that's it for this one.